Okay, so we will discuss bifurcations of 1D maps. Okay, so what is a bifurcation? So that's the first aspect we are going to look at. What is a bifurcation? So we understood so far in this course, we understood about 1D maps. 1D maps. Okay, so I don't. So okay. Uh, okay. So yeah, we will discuss about something known as fractals. What is a fractal? Okay. So as you know, I have shown you fractals in numerical method course. So fractals are self-similar objects that scale indefinitely over infinite scales. Okay. What does it mean? It means if you take a cauliflower and see the big cauliflower and you take pluck in say part of a cauliflower and zoom in that small part of the cauliflower, it will look like the bigger part of cauliflower. Okay. So in that way, a small cauliflower, a part of a cauliflower is self-similar to the bigger part of the cauliflower. Hence, cauliflower is a fractal. Okay. Whereas tomato is not a fractal. Tomato, if you chop off, everyone will know that you have chopped it off. Okay. Fine. So from where the term fractal came, so person who noticed it first that there is indeed a fractal geometry is Benioff Mandelbrot. Okay, so he was a computational scientist at IBM, and he discovered that there is something. So what rule or what geometry nature follows? Okay, what geometry nature follows? I mean, these are all man-made creatures where you see tables and chairs are rectangles or squares or circle. But what geometry nature follows? I mean, nature, the tree has a specific geometry which we don't know. Now, the clouds are not spherical, the clouds are not elliptical. The clouds have some kind of shape. Even the lightning, you see, the lightning strikes, they don't occur in a straight line. Rather, lightning occurs in a very non-trivial manner. Okay, you can't predict where the lightning will fall. Yes, and the lightning travel in a very sophisticated way. Fine. If you see the satellite images of Earth, it will show you the coastlines. The coastlines are very rigid and don't have a smooth boundary. Yes. So nature follows a totally different geometry in their natural phenomenon. So what kind of geometry it follows? So Benno Mandelbrot found that it follows the geometry of fractals. Okay. So fractal geometry, he is Mandelbrot. So these are his quotes. So which mentions that fractal geometry is not just a chapter of mathematics, but one that helps every man to see the same world differently. Okay. So clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, neither does lightning travel in a straight line. Okay. So to answer these questions, you need to know about fractals. So some of the examples is to appreciate the fractals is Jupiter. So the planet Jupiter, you can see on Jupiter that always people talk about this red spot. So there is a spot in Jupiter known as the red spot. What happens in this red spot is every time you see the red spot, there is continuous floods, okay, continuous floods and volcanic eruptions. So these are all volcanic eruptions and continuous floods. And these are so hot that these are the fluids. These are the fluids traveling in a chaotic way. So this red spot in Jupiter is actually a fractal. The more and more you go inside, the similar kind of geometry you will be seeing. Okay. So this is a fungus on the right hand side. You can see growing on the bark of a tree. So this is a chandelier fungus because it looks like a chandelier. Okay, and you can see that each branch is bifurcated into two branches. those two branches bifurcate into two branches, those two branches bifurcate into two. And like that, they repeat and they repeat. They use a for loop. It's like nature has used a for loop, isn't it? Nature has used a for loop and kept on iterating and generated this fungus. Okay. So that means nature is following a pattern and a geometry, and nature is itself a computational scientist to just compute and simulate. Okay. So, good idea. Now let us go a bit deeper. Okay. Yeah. So let us see into this veins. Okay, this is a part of the leaf. Okay, I hope you can see. This is a part of a leaf, and you can see how they are interconnected. How they're interconnected. It's not that simple. This is the network of veins. How fluid moves inside the leaf. Okay. So how when you water the plant, how using capillary action, your veins collect the water and the veins distribute the water throughout the surface of the leaf. And this is one of the reason why on the surface of the leaf you always find moist. Okay, it is always moist. So if you cover that with some a glass cylinder or something, that cylinder will be full of water droplets. If you can experiment this, what you can do is go to any plant, and the leaf of a plant, you just put one small polythene bag and tie it. So after 1 hour or 2 hours, you will see water droplets on the polythene, right? So what has happened? The water is from the surface is evaporated. So you can clearly see the self-similar structure. There is a certain rule, and using that rule, the geometry of the leaf continues to evolve. So nature is again simulating using a for loop. Okay. Another example is the six-fold symmetry you see in a snowflake. Okay. So this is a snowflake, and you can see this microscopic crystal structure of ice. Fine. And it is repeated several times. Okay. And it has a hexagonal symmetry. Fine. It has a hexagonal symmetry. And you can see that each of these parts, if my pen can work now, each of these parts you can see it here. This central part you can see here, 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 and this kind of hexagon you can also see it here also, isn't it? Okay. Now let us come to lightning strikes. So this image you can see is produced not naturally produced but rather man-made. This what is known as what you can do this is take a glass, and that glass you can pass it some metal copper wires and pass high voltage electric current inside the glass. So the current can flow through it. The current can flow through the glass, and what can happen, it can generate a huge pattern, and that's the pattern created by these lightning strikes. It is created by the voltage, the current. Okay. So you can see this image is produced by the high voltage electricity discharging through a non-conductive material, that is glass. And such kind of figures are known as this Lichtenberg figure. You can clearly see the self-similarity branching characteristic of a fractal in lightning structures. So you can see again nature is repeating in a certain way again and again. Okay. Fine. Same you can observe for these coastlines. So can you see in this coastline, this is a satellite image. This is a satellite image, and you can see that this is mostly frosty. I mean, mostly part of Antarctic region or something. It's cold ice, and but the surface are not smooth. I mean, I have drawn on yellow. It's a smooth line. Is it a smooth line? No, it is not a smooth line as yellow. It is something rugged and very rough. Okay, it is a very rough surface, isn't it? So therefore, these are all fractals. But it is not random. That's what I want to point it out to you, that do you see that the structure is random? No. If you see a small part of the chunk, you will feel that it is not random. It follows a branching kind of pattern. Okay. So therefore, the nature things are usually not random. It has usually a geometry and pattern to it. So same thing you can see using, even this is not in the macro scale, but even if you go to micro scale, you will see similar kind of structure. This is a structure generated by SEM. SEM, I hope you know, structural electron microscope. So, or transmission electron microscope, TEM. So this will help you to generate the microscopic images of any metal. And this is the figures of any metal. So you can see how inside these metals, you can see these kind of snowflake kind of structures in micro level. I mean in microscopic levels. So the fractals are not only present in macro level where you can see in trees and lighting, but at the same time they are hidden inside the micro level which you can see in microscope only. Or you need electron microscope to see them. So nature follows these rules not only in macroscopic areas but also in microscopic areas. So it is very strange how microscopic levels creatures are also advised to follow the same pattern. Fine. Another example is your video games. I hope many of you have played video games at least once. Okay. The 3D graphics. So in video games, you must be seeing there are trees, and those trees look like real trees. Okay. So how they have been generated? So the scientist or the graphic designer who have used, who have generated these trees or in video games have used to generate, have used methods of fractals to generate this image. Now, how to generate fractals? Okay, we understood this is a fractal, this is a self-similar object. So how to generate fractals? So you can generate fractal by hand, I can tell you, but it is very tedious process. Okay, better to use computers. The power of computer to iterate it again and again, 10,000 steps and generate a fractal. So to generate a fractal, we use something known as IFS. It is known as iterated function systems to generate fractals, okay? And also L system methods to generate fractals. Fine. And even fractals, as a child, I was seeing this in my household. Some figures are from my house. So you can see that we use this kind of drawings in festivals. And I have seen this in Kerala also. You use it sometimes in the corridors using flowers. What do you call that? Onam, but Puklam, yes, yes. So yeah, it was a good one. And yeah, in Odisha also we have this festival, and we take rice, add color to the rice, and grind the rice, and we get this different color powders, and we use those color powders to make this rangoli. This is like rangoli, and yeah. So this also has a geometry to it and very self-similar structures of fractals. Okay. And I suggest that, yes, one structure, and you can see the trees also. This tree you can see on the right hand side that it definitely has a structure. It is not at all random. So this guy, this is the main branch and it is branching to two, and these guys are branching into two, and they follow the pattern in every branch and they create this structure. Okay. And you see the pattern of the leaves also. They are not at all random. They follow a particular pattern. Even the broccoli on the left hand side is a very nice example of a fractal. Usually you find this abroad. Okay. So because this is very nice, because each small part, take this small chunk, pluck it out, zoom using your phone, take a picture and send it to a friend. So the friend will think that this is a bigger broccoli, not a small broccoli. Okay. So these are fractals, and this is a coastline. So you can see this is nature actually. This is nature coastline you see. And this is a smooth version of this natural image where each part is very smooth. Okay, not rough like this. And on the right hand side, you can see as a fractal, complete fractal, mathematical fractal. Okay, this is a complete mathematical fractal. So it is trying to tell us that natural things are not completely fractal or not completely smooth. They are somewhere in between. They are not either complete fractals, not also very smooth. They are somewhere in between. If you want to watch, you can go to 3 blue, 1 brown video of fractals and watch it. Very nice video. Okay. So you can see, so this is the motivation. So fractal geometry will make you see everything differently. So there is a danger in reading further. Okay. So why? Because you risk the loss of your childhood vision of clouds and forest, galaxies, leaves, feathers, flowers, and drops, mountains, torrents of water, carpets, bricks, and much else besides. Never again will your interpretation of these things will be quite the same once you have learned the fractals. Okay. So how you were drawing clouds in your classroom, like in your school days, I hope you remember how you draw clouds. But the clouds are not actually like this. Clouds are like, you can see the surface of the cloud is very rough. It is so rough that when an aeroplane flies inside the cloud, you experience turbulence. Therefore, when you are in the aeroplane and when you enter the cloud, you will see that you are facing a turbulence and your heartbeat is increasing. Okay. So that's the idea. And this has been said by Michael Barnsley, who itself discovered another fractal known as Barnsley fractal. Okay. So where this fractal word was coined from? So the fractal word was coined from the Latin adjective fractus by Maynard Mandelbrot in 1977. And that time no one believed Mandelbrot, and no one believed him that it is a fractal. And many people were saying that this is just a philosophy. It cannot be a fractal. And what he did is in IBM, he was in IBM, he used his supercomputer to create the first ever word fractal. Okay. And he showed and derived all the properties of that fractal and coined the word fractal to the whole. And since then, the whole world started believing about fractals. Okay. So if IBM and he was not there, fractal would not have been discovered so far. That's one of the way. So Franger means to break, create irregular fragments. So I hope you can see that thing on the left, on that nearby that fan. You can see the surface, what has happened due to the water corrosion. That is like not uniform at all, right? Is this uniform? Do you think this is uniform? No. This has many breaks, many breaks. And I hope that you can see any place like, I don't know, if you encounter that break also, yes, that break also in the back side, it doesn't have a particular geometry also. It never is the geometry you are seeing on the back side is like this. No, never. If I want to draw it, I think I can draw it something like this. Any part I want to visualize. So something like this I can see, and it is rough. So we follow this, and even the lungs and the veins in your bronchioles, you can see they are structured in a very different way, in a very composed way. So these are fractals also. Your retina, if you see, if you take a phone and like not a phone, a microscope and zoom into your retina, you can see something like branchings. You can see something like branchings. And these branching here, branching, this is branching here. So these are all fractals here. So therefore, there has been a lot of study to understand lung cancer and all. They study that the fractal pattern of the lung should be preserved. The moment the fractal pattern of the lung is destroyed, then there is a chance of lung cancer. And MRI people, those who do research in MRI and all those, they study the fractal patterns to find neurosurgical disorders or health issues. Anyway, so these are the ideas. So maybe I can take an example from here and show you some fractal patterns. I hope internet is there. So let us see a popcorn fractal. Okay. So this is like a popcorn fractal, and you can see how these patterns are self-similar and repeating itself. Of course, these are all generated via simulations, computer simulations, but you can see how this small part is getting distributed throughout this lattice, throughout everywhere. This small part is everywhere. Okay. So if you want to study more, there is something known as I think we can search for any fractals. You can see these fractals here, like, so this is something which we will be experiencing. This is known as Sierpinski fractal. Okay. So this is Sierpinski fractal, and we next class we will analyze the dimension of a fractal. Okay, dimension of a fractal. I could have studied now, but I don't know. The pen is not working. Not this, but you can study the fractals of many other structures. Even a Pascal triangle, I hope you remember this. There is something known as Mandelbrot set. So, yeah, yeah, you can play around. Okay. Maybe we can watch a video also.
Recently, I found out that the High Desert Museum opened a new city called Patterns Play, Fractals and Nature.
Yeah. So actually, when I started my bachelor's of science, so what I did is I was uh, pursuing data structures and algorithms course, and it's a class strength of around 400 students. And 400 students, very big hall. Um, so I remember, I think 400 to 500 students in that class. It's a computer science department course, and I was taking that course, and there was a huge saying that out of 400, only 100 pass the course every year, and other 300 people repeat the course in summer semesters. Okay, and I want to be in that 100. I don't want to be in that 300. So there was a test, and we were struggling day and night. And what happened is I was in my hostel room, and we were three people in that hostel room, very tiny room. And I was there from Odisha, and one was there from Punjab, another one from Andhra Pradesh. Every different culture did not like each other. Okay, but still had to be roommates. But it was a fun ride, and all were studying data structures. I was a kid such that my timing was very regular. I will sleep at 9 p.m., woke up at 4 a.m. Okay, and others were studying till 1 a.m. at night. I was the one in the whole hostel to sleep at 9 p.m. with my bed sheet on my head. Okay, and many people were teasing me on that also. But jokes apart, like when I was reading about data structures, I gave the test, and I came back to home, and like anyone else, I was browsing Facebook, I was browsing all things, browsing YouTube, all things, yes. Then suddenly, this video popped to me. The video I'm trying to tell you here, where my mouse is TED Talk. The TED Talk by Manuel Brendelbrot. And after I watched this video, before that I was wondering what I will do with my degree. Okay, what I will do. Like I don't know what to do with my degree, and what course I will do, what project I should select. Now it was not like that at that time. Now every course has a project. There, just attend the course, write the exam, pass the course, go to next course. Okay. So I was not sure. No faculty was telling me which course to pursue, and it was quite interesting that I came across this video, and this video changed my direction completely. In a way that I started questioning what is a fractal and who is this Mandelbrot. And I went to library and I purchased a book, and I started reading it in such a way that I forgot to watch all movies also. So I was a huge fan of movies that time. I was watching Bollywood and Malayalam movies also, but I stopped watching all those and I concentrated on this. And there started my internship career where I applied in this area or different internship locations. I came to Kerala, I came to IIST. I met a professor there. He guided me to study the basic parts. So I spent 3 months of my summer studying the basic parts. Then I got next year an opportunity to go to ICTS Bangalore, like the branch of TIFR. Then I started doing simulations there. So there I met my PhD supervisor in disguise. I was not knowing that after 1 year I will be the PhD student of that supervisor. And luckily he advertised a PhD project. I went abroad for that. And I got much more explorations on that area. And now I can see that I have developed some techniques on myself. So this is like one of the ride in a career of a student. So sometimes a video can change your life. So that's what I wanted to tell. So don't leave out anything which you find interesting, and try to pursue that. Just that I want to. Okay, it's a 15-year-old video. I think that time I watched it during uh, 2015. I think I watched it during 2016. Yes. So 2016, it's almost 9 to 10 years back. But it's good that I'm again telling to you guys in front of my students. So just a tiny video in which Mandelbrot is talking about fractals itself. So this fractal dimension we will be computing in the next class. How you can find the dimension as 1.17, 1.33, fractional dimension. So I suggest that you guys watch this video. Okay. It's a 20-minute video, not too long. Okay. So you can watch this and it's quite interesting.